Okay, so now for the next circuit, handy circuit technique, and this one is called source transformation. So, alright, so first off, what is this source transformation supposed to do? Well, what it's supposed to do is if you have sources and sort of key combinations, you can easily manipulate the sources, transform them between voltage and current source and vice versa, and be able to manipulate your circuit into an easier circuit without ever really having to analyze much and break down the circuit into a much simpler circuit, and then eventually it will be very simple to analyze. So what we're essentially trying to do is figure out how can we do this. So let's look at a couple things before we figure out how this will work out. So let's look at an ideal voltage source. And let's, just call this V source here. And we know that if we are trying to put a voltage source and deliver a voltage to a load resistance like this, we know, okay, well, let's give a drawing of what V out versus, now this is a little bit of a strange diagram, versus RL. So RL is going to the right, and so it's like our x-axis, and V out is our right axis, or y-axis, excuse me. Well, here is V out that I'm looking for. So what is V out? Well, okay, these two are just in parallel, so V out is always going to be V source. It doesn't matter what RL is. So what this graph will look like is a straight line that is horizontal. It doesn't matter what RL is, V out is going to be equal to V source, whatever that source voltage is. Okay, but what if we change this up a bit and say we have a practical source, one that has a resistance associated with it. So now we have V source. We're going to have a resistance RS, and okay, we still want to look at this load resistance here, RL, and I'll call this voltage here still V out. I'll also call it VL. And so now what I'm sort of saying our source is not just V source, because that's the ideal source. Our source now is really a combo of the source, the ideal source V source, and RS, the source resistance. That's why I called it RS. Okay, well, let's say that we have current IL flowing there. We can figure out what V out is, or VL, whichever way I want to say it. V out, this is just a simple voltage divider law. V out is equal to VL, and that's equal to RL over RL plus RS V source. Okay, and so now let's draw this graph of what V out looks like versus RL. Not RL approaches 0. Why did I say that? I have no idea. So V out. Well, when RL is low, now see this is not going to be the same. When RL is low or 0, we get 0 out. So that's down here. When RL is infinity, we get infinity over infinity plus RS. Well, the denominator is still going towards infinity, so we'll get infinity over infinity. That goes to 1. This is not the best math procedure, but we can see in the limit that's what's going to happen. So we'll get VL is just V source. So up here is just, I'll call this towards infinity is V source. Well, when RL is equal to RS, we can see how does this relate to V source? Well, this is excuse me. V out is linearly related to V source, and so the nice thing will be when RL is equal to RS, the source resistance. So I'll just put this right here. Well, maybe not right there. That was not a good. About right here. RL is equal to RS. The two are the same, so I'll get RL over RL plus RL. So RL over 2RL. So the RLs will cancel and I get half V source. So here's V source over 2. That will be the value. This was trying to draw it so it was in the middle. So we get a graph that looks like that. RL tends to infinity, we get V source out. RL tends to 0, we get 0 out. And we get this straight line. Okay. I also can say here, what's IL in this case? IL is V source over RS plus RL. I made a mistake, so I'm coming back to correct this. I actually think I said the right thing, which is that the output voltage here is a linear function of the source voltage here, and it is, and it's a slope with straight line RL over RL plus RS. And that's fine, but I think what I did was I actually, in my drawing, I had V out versus RL here, and I said, okay, let's copy this over to a new page. I said when RL equals 0, I can plug in and I'll get 0 over 0 plus RS times V source. So that's VL equals 0. So that's this point right here. And then I said another important point is when RL is equal to RS, and that is RS over RS plus RS V source, and you can see that this makes VL go to RS over 2RS V source, or that could be just simplified as V source over 2. And so that's why I put this point right here. And then I said, okay, as RL approaches infinity, that we would have infinity over infinity plus RS. And as I said, this is not the greatest math in the world. So infinity is going to dominate in the denominator. And so we're going to have basically infinity over infinity. So that's going to be 1. And so VL will approach V source. So that's what happens as we approach infinity. And then for whatever reason I said, okay, so here, and maybe I'll just draw this as an asymptote. And so not actually show that point like at infinity, because obviously we can't get there. Okay, so what is actually going to happen is, how does this curve vary? Now this is really more detail than I wanted to say about this topic, but since I actually did it crazy and drew a line, then I feel like I need to point out a little bit more about it. So maybe the first thing we should do is take the derivative of VL with respect to RL, and that'll tell us what the slope looks like. Now, I can look at this and I can say, oh, okay, that's going to give me I'll do stuff like bottom RL plus RS times the derivative of the top. So I'm just calling it VS here, so I don't have to continue writing V source everywhere. Minus the top, so RL times V source, times the derivative of the bottom. Well, the derivative of the bottom, derivative of RL plus RS, is just 1. So have that over the bottom squared. And if I look at this, I'll have RL times VS minus RL VS, so those two will cancel. So I'll get RS VS over RL plus RS quantity squared. Now notice RL and RS are resistors, so as long as we're considering positive source voltage there, which, I mean, that's the way I've drawn it for V source, so that makes sense. And if we think about this derivative here, that tells us what the slope of that curve should be like, and so that's saying right here this should always be positive. So, and I'll say for positive VS. And then I can take the second derivative. So notice what that says is the slope should be positive. So we can think of this or this or this or this, but the slope of the curve should not look like that, or the curve should not look like that, because the slope would be negative then. So that's not a possibility for that curve. Now if I want to take dVL d squared VL drL squared, the second derivative, I can do that, and so I'll have I'll have bottom times the derivative of the top. Well, the derivative of the top doesn't have the top doesn't have RL in it anywhere. It's just RS VS. So since the top doesn't have RL anywhere, the derivative of it is 0. So bottom times the derivative of the top is going to be 0 minus the top, so RS VS, times the derivative of the bottom. Okay, we need to use the chain rule here, so we'll have 2 times RS plus RL to the first power times the derivative of what's inside with respect to RL, and derivative with respect to RL, well, derivative with respect to RL of just RS is 0, derivative with respect to RL of RL is just 1, so we're left with 1, all over the bottom squared again. So RL plus RS squared, so that's to the 4th power, and this gives me minus 2 VS RS. RS plus RL in the numerator cancels out with one of the 4 that I have in the bottom, so I'll have RL plus RS cubed. Notice RL and RS are always positive, they're resistors, so RL plus RS cubed is always positive. RS is positive, we're again considering positive VS here, so this slope of the slope is negative. So if at first we start with a certain slope, as we start to increase RL, what that means is the slope is going to decrease. That's what the negative stands for. So what our plot would really look like here is something more like this. And as you go towards infinity, maybe that's not my best curve in the world there either, but the slope has to start out the most positive it's going to be, and then it's going to decay slower and slower and slower, and as we get towards infinity, the slope is going to go towards 0, and we're going to approach this value of V source. So it doesn't look like a straight line at all, like I had drawn. Don't ask me really why I did that. I think my mind was off somewhere else. So anyways, that is what I was trying to show. I'll insert this in between where I had started talking about it, and see if we can't figure out how that's going to relate. So a practical current source is going to have a source current, which I'll call, just make it simpler, not write I source, I'll just say IS. And then I'll call its associated resistance RP for R parallel, but it's still the source resistance. And we're going to drive the load resistance, RL, over here. And we're going to have VL, and IL is going through the load. Now notice it is not going through RP, it is just going through the load resistance there. And so our source in this case, excuse me, is there. So it's similar, but now you see the resistance is in parallel with the current source. Well, okay, if we want to solve for, and maybe I should say, again, what is the point of this? We want these two sources to deliver the same voltage and current to the load. If they deliver the same current and voltage to the load, then what can we say about the two sources? We can say they're the same, or they're equivalent. So that's what we're trying to do. And so IL, oops, excuse me, go back to my black. So IL in this case is going to be the total current IS using current divider law. We'll get RP over RP plus RL. And VL, well, VL is just IL times RL. And so that will be IS RP RL over RP plus RL. Alright. So now let me say, or write down in words what I just said. So we want these two sources to be electrically equivalent. And what that means is, so we want VS and RS to be somehow equivalent to IS and RP. And maybe I should be careful, that should be really V source. I'm going to erase that, but that's what we're really saying we want here. So, to do that, we need to match the load voltages and load currents that they deliver. So the VL and IL that they deliver to RL. Now I'm just going to say if I let RS equal RP, okay, if I do that, then VL that I got for the first one, what was it? VL was RL over RL plus RS V source. Now I'm just going to make that simpler and just call it VS now. So I just have that. And for the current source, I had that VL was IS RS RL, right? IS, excuse me, maybe I should put RP RL, but remember I'm going to say let RS equal RP, so I'm going to do that in this one. So RP, maybe I'll just write it this way, RP RL, I'm going to say substitute that for RS over, I guess I'll just say again RP plus RL here. I'm going to make that RS. So notice that if I do that, I'll have RL over RL plus RS VS, and I'll have RL over RL plus RS, but then I'll be left in the numerator, I'll have IS RS, right? So I'll have that term that's left over, this RL, and the bottom became RS plus RL. So we have two things, and we can see, well, okay, the voltage will be equivalent and we'll get the same value if VS, see, this is the same and this is the same, so if VS is equal to IS RS, then those load voltages are the same. And now notice that's we can get the current. We know if the load voltages are the same, the load current is the same, because in both cases IL was just VL over RL. So if the voltage is the same, the current's the same. We don't have to worry about that here. So what this means is that, okay, if we have that source voltage is equal to the source current times the source resistance RS, and maybe I should say that could also be written as IS RP, since we let RS equal RP. So the voltage source is equal to IS RP, or IS, the current source, is equal to VS over RS, which could have also been VS over RP. So this tells us how we relate the value of the current source and the voltage source, and we let RS equal RP. So let me point out here, what we have done is we've said, okay, if I now have VS and RS, and that ideal, excuse me, not ideal, if that practical voltage source is attached between terminals A and B, I can replace that with a current source with current value Is, which is equal to that Vs over Rs, and in parallel with it I need to replace its resistance with a parallel resistance Rp, but its resistance is actually equal to Rs. And if I do that, then these two things are equivalent to each other. And so that means I can replace them. And also note here, the load voltage and current are the same for both of these. Since the load power would be VL IL, since I use the current IL is going from plus to minus, then since the power is equal to that, and the voltage VL and the current IL are the same, then the power is the same with either source, which of course we would hope, because they wouldn't be equivalent if they weren't. Okay, so let's do an example here of source transformation. All right. So we'll have 5 volt, 1 ohm, 2 volt, 4 amp, 1 ohm, 2 ohm, 5 ohm. And let's say what we are after here is what's the power absorbed in the 5 ohm resistor over there. Alright, and we're going to use source transformation to do this. I mean, obviously, you know, with what we've known now, what we really need to do is either calculate that voltage V5 ohm or the current I5 ohm, either one, and we could find the power absorbed in that 5 ohm. So that's all we really need, and we could do the circuit with everything that we've known so far. We could write maybe 3 loop equations, or maybe we could, you know, do nodal analysis, whatever. Doesn't really matter, but we could do it already. But how do we use source transformation to sort of help us through this in a quicker way? Well, the first thing you might note here is, okay, we've got here 2 voltage sources in series, and we've already talked about how can we handle 2 voltage sources in series. We can just add the two, and so since it's 5 plus to minus, I'm going to keep the same reference there. Notice the 2, you know, I'm going, as I go from here and around, I would go from minus to plus, and then this one would be plus to minus. So the first thing that I would really say is, okay, well, that is the same as minus to plus minus 2. So now they have the same reference direction, and so my net, if I come here and start my analysis, excuse me, well, okay, so my net would be, I'll come over here, this will not be 5 anymore, it will be 5 plus a negative 2. Which is equal to 5 minus 2 is 3. So this whole thing is now a 3-volt source right there. Okay, now that wasn't source transformation, that was really just combining sources. But now here's where you can start to see source transformation. And we're going to do source transformation and combining sources together again here in just a second. So generally, what's your clue that source transformation would be a good thing to use? Well, it's the fact that you would have a voltage source in series with a resistor or a current source in parallel with a resistor, and somehow we can translate those and combine to something, and combine two other things. So what I mean by that is I'm noticing right here that if I look at this particular setup, if I do a source transformation, I can call this terminal A, down here terminal B, that if I use this source transformation technique that I just learned about, I'll get a current source in parallel with a resistor. So that means if I come down here, I know that I'm going to get a current source in parallel with resistors. So here's my A and here's my B. Okay, well, what's that current source equal to? Now this is one thing to notice. Okay, I have drawn, when we look at my theory over here, how are the sources equivalent? The plus goes where the head of the arrow is. So the plus going with the head of the arrow says that the value of the source is going to be Vs over Rs. Okay. I have drawn, so here's plus, here's minus. Well, I drew it on the wrong one, but here's plus, here's minus. So my arrowhead is going to go the same direction. My head is at the plus, tail is at the minus. Okay. And its value is equal to the value that I have right here, which is plus 3, so 3 over 1, because that's the resistance Rs. So just to make it clear, this was Vs, this is Rs. So source transformation says that this goes to a 3 amp source, and this is equal to Rs, and that was equal to 1 ohm. Okay, now you can hopefully see what makes source transformation nice. Notice I didn't have to analyze any circuit really, it was pretty simple, but now notice I've gotten into the spot where I have one interesting thing here, and that is I've got this source and this source, which are both current sources, and they're in parallel, and we talked about how we could add those parallel current sources previously. So what that means is I'm going to use that same plus arrow reference direction, or the head of the arrow on top. So I'm going to change this one just to be consistent with what I have done in the past. I'm going to change this to an arrow going up and call it minus 4 amps. It's the same thing, I just changed the reference and changed the arrowhead, or changed the arrowhead and then changed the sign of the source. So now I have a 3 amp source going up and a minus 4 amp source going up, and so my net is going to be, take this out, 3 amp minus 4 amp, or minus 1 amp. Okay. So again, still no, I haven't written any equations yet, none at all. And so now I'm going the next step. Okay, I have negative 1 amp and 1 ohm resistors, so I'm going to go back and do a source transformation, and I'm going to have plus to minus, okay, so here's my A and B. And maybe I should be careful because I've kept these labels there, and that doesn't exactly make sense because I've added sources and so forth. I think it may have been okay to do, yes, it's okay to do up to that point, but I shouldn't have called this one still having A and B. Okay, so if I have this A and this B, and I want to convert it back into a voltage source and series resistance, my voltage source value, okay, my voltage source value, going back and looking this, well, if IS is VS over RS, then VS needs to be IS times RS, or IS times RP, whichever one you want to say. So that's going to be minus 1 times 1. So it's going to be minus 1 volt, and we're going to move the RS that was right here up to being in series. So here's 1 ohm. There's that part of the circuit, and attach the rest of the circuit here. Alright, so now we can see that that resistance right here was 1 ohm. Well, we've got two resistors in series, so we can easily add them together and get a 2 ohms series resistance. So now I'm going to have my minus 1 volt source, 2 ohm, so here's the 5 ohm, here's the 2 ohm. Okay, now again, I'm going to relabel and say, okay, now I'm going to do a source transformation. I'll call this terminal C and this terminal D. And so I'm going to do source transformation. My current source, I'm going to keep the arrowhead at the plus, is going to be minus 1 over 2. So minus 1 over 2 is going to give me minus a half an amp. And then I'm going to put the resistance that was in series with it, I'm going to put it in parallel with it, so 2 ohm. So here is C, here is D, And then I've got my 2 ohm. And my 5 ohm. Well now, okay, clearly the 2 ohm and the 2 ohm, you know, that are right here and right here are both in parallel. So I can go ahead and, manipulate them. 2 ohms in parallel are going to be 2 times 2 over 2 plus 2, or just half of 2. So that's 2 over 4. Excuse me, 4 over 4, which is 1. So I'll have minus half an amp one ohm, and then 5 ohm. Okay. And then, obviously, my goal was to find V5 or I5 ohm. Can just use current divider law, and that will give me I5 ohm is equal to the total current. So the current coming in here in that branch is minus half amp. And so to use a current divider, I need to do times the resistance in the branch that I don't want to know it. So 1 ohm is the resistance in the branch I don't want to know it, over the addition of the two, 1 plus 5. So that's equal to 0.5 divided by 6. So this is minus 0.083 bar over it, milliamps. And so if I want power absorbed in the 5 ohm, I could go find V, but hey, I already know I, so I'm just going to use I squared R. So that's going to give me minus 0.083, the bar over it squared, times the 5 ohm, and that is going to be 0.3472 with a bar over it. Oops, excuse me, 0.03472 with a bar over it. So 34.7 milliwatts. Okay, so that's our example for source transformation, and I hope you can see that that is a little bit of a different technique than one of the ones we use most of the time. It's more of a look at the picture and manipulate a picture and change things from series to parallel, parallel to series for voltage source and current source and so forth, and a little bit less of the circuit equations kind of analysis. So it can be nice, and it's a little bit of a useful technique, especially when you can notice when you can combine sources and or resistors by using source transformation. Okay, so that's it for day 6's lectures, and see you all in class tomorrow.